Okay, continuing on. So, we did step 4. We found the function. We found the interval of possible values. Step 5. Find the derivative. And actually, I'm going to copy my original function down again, just so it's on this piece of paper. Recall area equaled 375x minus 5 halves x squared. So A prime is going to be 375 minus 5x. Find the critical numbers. On the interval in question, so in this case 0 to 150. Again, at the calculus 1 level, that's not going to be a particular issue. The critical number you find is always going to lead to the answer, just because that's the way they wrote the textbook. In real life, maybe you're not going to find a critical number in the required interval. It can happen. Won't happen in calculus 1, but it can happen in real life. So I set that derivative equal to 0. And so I get negative 5x equals negative 375, and x equals 375 divided by 5, 75. That's what we think the answer is going to be, or what's going to lead us to the answer. But all we know for sure is this is a critical number. It can be a local max or a local min or nothing. That's all we know mathematically. It can be a local max, a local min, or nothing. So you must verify. So we must verify. In this case, if we go back to the original problem, we wanted the largest possibility. Must verify it will lead to a maximum. So step 6, verify maximum status on my interval from 0 to 750. Now, like I said, when we began began doing these problems, I said that I wasn't going to freak out if you didn't do the optimal way of doing the verification. I just want to see that you did something to verify. Now, what's optimal on a closed interval? What's optimal is that we will use the procedure for absolute max-min. So now we think back several sections to what was the procedure for absolute max-min. Okay, so the procedure for absolute max-min on a closed interval was find the derivative, find the critical number. We did those two things. Then, after you had your derivative and critical numbers, as the case may be, here we just have a critical number. But after you had your derivative and your critical number or numbers, you then took the original function which in this case was a equal 375x minus 5 halves x squared, and we find a of 0, a of the critical number, a of the endpoint. That was the procedure for absolute max-min. After you had your critical number, you took the original function and you found the values at each endpoint and the critical number. If I plug in 0, I'm going to get 0. And if I plug in the 150, you're also going to get 0 because that's how we actually figured out that 150. The 150 was where y went to 0. Now again, that's because this is Calculus 1, and that's the way the problems in Calculus 1 always work out to be. It doesn't have to be the way the real life is. Then a of 75. That's going to give us my calculator will cooperate 375 times 75 minus 5/2 times 75 squared. And if I've pushed all the correct buttons, I'm going to get 14,062.5. I'm going to allow us decimals here just because I feel like it. And also just because, yes, I could call that, I could change that to a fraction, but that's not the way we communicate those sort of things in real life. If the farmer said, you know, how big it is, should it be, you're not going to say it's going to be 3/4 of a whatever. I'm going to let you go with decimals. But clearly, that is my maximum. And so now I have just proven that x equals 75 will lead to a maximum. So step 7, answer the question. And so way back when we started this problem, what is the largest area? And it's not x equals 75. Remember what x was its vertical distance. So whatever x was not the answer here, but it led us to the answer. There's the answer, the largest area is 14,062.5, and this was measured in feet, square feet. And there's our first optimization problem. Okay, let's start the next one. A closed cylindrical can is to hold 1,000 cubic centimeters of liquid. How should we choose the height and radius to minimize the amount of material needed to manufacture the can? So I've read the problem, so now we're going to draw a picture. Draw a picture. And so it says a closed cylindrical can. So the best of my abilities to draw something that looks like a can. There's the top. There's the bottom. Didn't do such a good job there. And it says, how should we choose the height and radius? So let's have a height and let's have a radius. And I'm going to name that H and R. So there's my picture. 3, my constraint. My constraint here is holds 1,000 cubic centimeters. And then we get to decide what that means mathematically. And your units can give you clues sometimes. Cubic units measure volume. So what they've told us here is that the volume equals 1,000. Now mathematically you go and look this up, and the same things when we did related rates. I expect you to know about squares, rectangles, boxes. So that would be, for squares, rectangles, and boxes, that would be area, perimeter, surface area, volume. I expect you to know about circles. So that would be area and circumference. Right triangles, so that's going to be area, Pythagorean theorem, and trigonometry. Expect you to know all those things. Cylinder, don't expect you to know it, so you can look this up. The volume of a cylinder is pi r squared h, and that's going to be 1,000. Solve for one of the variables, solve for whichever variable you think is easiest, and in this case, it's easiest to solve for h. So there's my constraint. And then step 4, we are supposed to minimize amount of material needed to make the can. So we got to decide what that means. So the amount of material that they needed to make, we'll call it the side of the can, top and bottom. All the stuff to make all those surfaces. The surface of the top, the surface of the bottom, and the surface of the side. Surfaces, this is telling us to minimize the surface area. So now we got to decide what surface area is. Surface area of a can. Well, that would be the top plus the bottom plus the side. Well, the top and bottom are both circles. Area circle, area circle. The side, however, I'm going to try to do something here. I don't know how well it's going to work. This paper shuffling here is me trying to fashion a can out of paper really quickly. Okay, so there is my can. Top, circle, bottom, circle, and then we got side. So there's my can. Now let's cut open the can and see what we get. So here I'm going to pretend I'm going to cut open the can. Here's my can. You can see a pretty good visual of the can there. There's my can. I'm going to cut open it and I'm going to unroll my can. Well, when I cut open and I unroll my can, there's the side of my can. The side of my can is just a rectangle. Here it's a rectangle. Now it's a can. And so my side, so now it's a can, or in reality it's a piece of paper folded into a cylinder. But when I cut open my can or my piece of paper folded into a cylinder and I unroll it, I've got nothing but a rectangle here. So my side is the area of a rectangle. Well, area of a circle, my radius up there is still pi r squared plus pi r squared. Now, back to my can. Okay, so here's my can again. And the height is just h. The height of my can is h. When I unroll it, there's my rectangle, h. But then I need to know what this, I want the area of this rectangle here, so I need this distance. This is height. I need that distance down there. And we're almost at 15 minutes, so I have to end this video. So cliffhanger, we're going to find out what this distance is here on the next video.